Right, welcome to 9.5. So today we're going to talk about properties of logic. So a lot of these properties are going to seem familiar to you because you've seen these words before. So you should remember a lot of these properties from set theory. So now we're just applying it to another application of this course, which is logic. So starting off with our regular symbols. So I just want to make sure that we're all remembering what these are. So we have conjunction, right, which was also known as and, which had that upwards arrow. We had disjunction, which was or, and that was our downward facing arrow. We had negation, which was not with our words and had that squiggly symbol. And was not and or NAND, right? And that was our and symbol with the complement over top. Nor was our not or, again, our or symbol with the complement over top. Exclusively or, we just said or, we called it. And that was our or with the kind of complement symbol on the bottom, right? That was when we had exactly one true. Conditional, remember, was the arrow. That was our if then. Biconditional was if and only if, right? That was the symbol for if and only if, and we had the double arrow. So again, kind of going through what was required for each of these for our truth table, and was we needed at least two truths, or we needed both to be true, or we needed at least one true. Not was just the opposite of the previous column, or whatever column we were negating. Not and was the negation of our and column. Not or was the negation of our or column. Or, exclusively or, was when we had exactly one true. If then was true when we had true implies true or false implies anything. If and only if was true when you had both values the same. Okay, so those are all the components of what we've done so far. So now we're going to kind of relate those to our different properties. And again, these should seem super familiar because you've done them all before in set theory. So the commutative property, this is for any statement P and Q. We have that P and Q is equivalent to, right? So biconditional with Q and P. So this is, remember for set theory, it meant that the order doesn't matter, whether you do A union B or B union A didn't make a difference on the outcome of your set. So same thing here, whether you do P and Q or Q and P, you're going to get the same values, right? Because we're only looking for when you have both true. So same thing for ors here. We can do P or Q if and only if Q or P. Or so and or are equivalent statements when you change the order. Okay? So associative, if you remember the associative property from set theory, that said that if we had three components, so three simple statements or three sets, and you're doing the same operation between all three, it doesn't matter which kind of chunk you do first, right? So if I have P and Q and R, so if I do the P and Q first, right, that's equivalent to, it'll have the same final column if I do P and Q and R. So it doesn't matter which grouping I do first, which part I put in the brackets, if all the operations are the same. Okay? And same for ors. So P or Q, I can do that chunk first and then take an or with R. That's going to be the same or is equivalent to P or Q or R. Right, that's our associative property. So I'm just going to take a second to prove one of these with our truth tables, right? Because we know how to prove the equivalence. So if I said prove the equivalence of the associative property for, let's do or, right? So if I said prove that property. So remember that when we're doing a proof, when we're trying to prove equivalence, we have to use this entire statement. So we're showing that the left side and the right side are equivalent by connecting them with a biconditional. So I have three simple statements. So I have P, Q, and R. Right, so I can fill this in. True, 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 true. False, 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 false. Q is going to be two trues, two false, two trues, two false, and R will be alternating true, false all the way down. Okay, then we can fill in our connective. So if I'm working with the left-hand side here, first I need to figure out P or Q, and then I need to do P or Q or R. If I'm working with the right-hand side, I'm going to do Q or R, and then P or Q or R. And then this is going to be everything. So all indicating P or Q or R. This is my biconditional, right? Biconditional with my P or Q or R. Okay, sorry, my biconditionals are looking sloppy today. Okay, so filling in our truth table here. P or Q, so going through my first two columns, anywhere I have at least one true. So my first half is going to be true because my first half of P is all true, and then I'm going to have two trues for my next two rows, and then the last two are just false. Okay, so P or Q or R. So now I'm looking at these two columns here right next to each other, and again, it doesn't matter whether I look at R first or P or Q first, because that is also our commutative property. Right, so just looking at these two columns here, anywhere I have at least one true, so going down row by row, everything but the last one. Right, everything has a true except the last one. So Q or R, so now I'm looking at these two columns here. Again, anywhere that has a true, so as we're going down, so I'm going to have true, 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 false, true, 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 false. And then P or Q or R. So now I'm looking all the way to my first column and this one here, so it's kind of tricky to go back and forth. I know the first half of my P is true, so I can already just do the first half being true. And then for the last four, these ones are all false, but I have true, true, true. And with true, 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 and a false for my last two being false. So again, we already know that these are proven equivalent because I'm looking at the two columns on either that represent either side of my biconditional, which is this side here that shows me this column, and this side here which shows me this column. So visibly I can already see that these are equivalent statements because I have the same columns. But I'm going to do my last column here to prove it, to show with a biconditional, to fully prove something. I need to show that biconditional and get that tautology, right? So my last column, I'm looking for a biconditional, which means my two values on either side of the biconditional have to have the same value. So they don't have to be true, they just have to be the same. So true and true gives me a true, true and true gives me a true, true and true gives me a true, false and true. Uh-oh, it looks like I made a mistake here. Q or R for this one has two false. Oh, that's why. Sorry, I'm looking at these two columns, and I even did the orange arrows for them. So we have true and true, 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 false and false. So all the way down. There we go. Sorry, I'm pre-recording these, and I'm starting this way earlier than I normally do, and I haven't had any caffeine yet. Okay, so we have our tautology, right? We know it's tautology, so therefore these three dots can be replaced of the word therefore. Therefore, I can put proven, or I can put shows equivalence, or property proved, whatever. So I have therefore proven. Right, so again, that was just proving our associative property, which we know is going to be true because we know it's one of our generic properties that we use both in set theory and now in logic. Okay, moving on to some more properties. So we have the identity properties. So if you recall these from set theory, the identity property, if T is a tautology, C is a contradiction, and P is any statement. So we've kind of already looked at these ones already. Right, T is always true, C is always false, and P is any of our simple statements that could be either true or false. So our identity properties are P and T. P and T is biconditional with P. So a simple statement and a tautology will always be equivalent to a simple statement. P or C is biconditional with P. A simple statement or a contradiction will always get you back to a simple statement. So we can prove these by drawing up some quick tables showing our biconditional. So we did an or last one. Let's do an and this one. So let's prove this property here. Right, so if I just wanted to do a makeshift table for myself, I know I'm going to need P, T, P and T, and P and T biconditional with P. Right, so I know I have a simple statement to start, and the rest of them that I'm working with is a tautology. So I only need 2 rows. Right, I have one simple statement, so I'm going to have 2 rows. So it's going to look something like this. Right, this is going to be true or false. My tautology will be always true. P and T. Right, P and T is going to be true here and false here because I have that false. So P and T, biconditional with P, so true and true is true. False and false will give me true because they're both the same. So I get that tautology, so I know that these two statements are equivalent. So that biconditional proves those two statements are, those two statements are equivalent, okay? So you can do the same thing with P or C and check that you're getting P is correct. So if you want to pause the video and try that one, you should have enough space if you're using my note to do it right there. So just pause and try it. Make sure you get back that tautology, right? So when we did these ones before, when we looked at them before, we said that P and T is the same thing as getting a simple statement, right? So we looked at P and T and we said that true and false is the same thing as a simple statement. So I could say that P and T is equivalent to P, right? We could say is equal to or is equivalent to the simple statement P. But to prove that that whole property is always true, we want to get it as a tautology. So instead of just saying is equivalent to, I toss it in with that biconditional and I prove it with that tautology in my final column. So kind of the same thing that we did, I think last week, but this is our better way of doing it now that we've learned more skills with our conditionals and biconditionals. Okay, distributive property. So we have P, Q, and R again. So remember the distributive property uses 2 operations or 2 connectives. Okay, so we have P and Q or R. All right, so this is going to be my left-hand side. And we're going to say that this is equivalent to P and Q or P and R. Right? And because it's equivalent to, I'm going to prove that by tossing those two compound statements together with a biconditional. Okay, and we can do the same thing with the opposite connectives. So I can do P or Q and R, biconditional with P or Q and P or R. Right, if you kind of remember, this was like when we expand something into brackets using our basic algebra. Okay, so those are our distributive properties. Again, they should look very similar to what we did in set theory. If I want to prove one, let's go with the first one. So we're going to have P, Q, and R First half true, second half false. For Q, we have 2 true, 2 false, alternating the way down. Again, making sure your T's and F's are clearly written. And R, we're going to alternate true, false all the way down. Okay, so now layering in our connective. So if I'm starting with the left-hand side, I have P already. I can't take this and until I have that inner bracket. So I'm going to do Q or R, and then my P and Q or R. That covers my left-hand side. Working with the right-hand side, I'm going to do my P and Q. I'm going to do my P and R. I'm going to connect those with an OR, so P and Q or P and R. So that covers everything on the right-hand side. And then my last column is going to be everything together, so that's my biconditional. So this is where I'm looking to get that tautology to prove that my left-hand side and my right-hand side are equivalent. So going through my answers now, Q or R, so looking at my second two columns here, or means we need at least one true. So we're going to have true, 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 false, true, 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 and false. Combining that last column that we just completed with our very first column true, P and Q or R. So I'm connecting this one and this one with an and. So now I need both values to be true. True, 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 false, 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 false. Okay? And then we're going to work with our right-hand side now. So we have P and Q. True, true, false, 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 false. Right, P and Q. Now P and R, we're going to have true, false, true, false, 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 false. All right, remember we're connecting with an and. Just going to double check here. It's easier if you put your fingers on the columns as you're going down for your handwritten work. So it's a little bit more difficult to do this online, but you'll be writing these on paper in front of you when you do it on your test. So you will have the opportunity to be in the table to kind of go through it. So P and Q, we had true, true, and everything else is false. Good. P and R, we had true, false, true, false, 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 false. Okay. And then connecting those last two columns that we just did are P and Q, P and R. We're going to connect those with an OR, just like we have in our right-hand side. So we're going to have true, 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 and false all the way down. Right, so again, we can check right now to see if we have equivalence or if we're going to get that tautology. Right, we're going to use our right-hand side and left-hand side. Those two columns I can already visibly see are the same, right? Which means when I connect them with a biconditional, having those same values is going to give me true all the way down. And I can say that the distributive property, ooh, that's not how you spell it, distributive property for our first one here is proven. Okay, we do get that tautology. Okay, so moving forward, we do have a few other properties. I know the homework questions in this section kind of go through all the proofs for all the properties. So you will have the opportunity to try all of them. So I'm not going to do many more, maybe a couple more. We have the idempotent property. So if you remember that one, it starts with one set, uses another set, and gives back the same set. So same idea here. We start with one simple statement. We use the same simple statement, and we get back the same simple statement. So we have P and P will be equivalent to P, or is biconditional with P. Or if I have P or P, that's going to be biconditional with P. Okay. Think true and true will give you back true. False and false will give you back false. Right? True or true will give you back true. False or false will give you back false. So we can already kind of see that those ones are equivalent. The double negative property, right? So same with our complement property. If you have the negation of P and I negate it again, so the negation of a negation is just going to get you back to your original P. Right? So the negation of P will get you back P. So if P was true and I take the negation, it's now false, and I take the negation of that, it's back to being true. So we get what we started with. Same thing if it started with false, I take the negation, it's now true. Take the negation again, it's back to false, and that's what we started with. So is equivalent to or is biconditional with P. De Morgan's, one of our favorites, as I'm sure you're aware. De Morgan's, we have the negatives, or the negations, right? So if I have the negation of P and the negation of Q, right, that's going to be biconditional with, and if you remember your De Morgan's from set theory, right, that's the negation of P or Q, right? So you can pull that negation out, or you can pull that complement out, and you flip your operation from union to oh my goodness, I'm blanking. Union to intersection or back and forth. Okay, so that's De Morgan's one way. The other De Morgan's, right, if I have the negation of P or the negation of Q, that's going to be biconditional with the negation of P and Q. All right, so I'll leave you that one to prove in your homework. That's a nice one to kind of go through. We have tautology contradiction properties. So again, T is a tautology, so always true. C is a contradiction, so always false. And P is any simple statement, so either true or false. So we have 4 different properties for this one. So if I have P or T, so we did P and T, right? That was up here. P and T was always a simple statement. But if I have P or T, right? If I have P or T, so true or true will give me true. False or true will also give me true. So we're always going to get back a tautology. So P or T is biconditional with a tautology. Our next one, if I have P and C, and you can always just give yourself a quick table to make sure that this property is true or to verify the property. So P and a contradiction. So again, if my simple statement is true, we're going to have true and false, which will give me false. And if I have P as false, false and false will also give me false. So I'm going to get back a contradiction. Okay, and then the other 2 properties here, if I have P and the negation of P, right, so this would be true and false, or false and true. Either way, if I'm taking that with an and, we're always going to get a contradiction. And if I have P or not P, right, true or false, and false or true, we're always going to get back that tautology. So those are your 4 kind of tautology contradiction properties. The difference between those 2 and the other ones that we did, right, the identity properties gave you back P. Right, they gave you back the simple statement, whereas the tautology and contradiction properties, as you can see, they give you back tautologies and contradictions as our answer. Oops. Okay, again, any questions, pop into our live session. We're just going to go through maybe one example of these, doing the table on its own. Maybe we'll do 2. We'll do P and C biconditional with C, and we'll do P or not P biconditional with the tautology. So let's prove those 2, and then the rest I'm going to leave you for your homework. So P and C, again, we have one simple statement and contradiction. So if I only have one simple statement, I'm going to need 2 rows of data. I'm going to need P and C. And I'm going to need my last column. Oops, sorry, I'm going to need C as well. Let's get that first. C. Then we'll do P and C. And then we'll do P and C biconditional with C. We have this column, a little messy, but it's there. Our contradiction, false and false. P and C, so true and false is going to give me false. False and false is going to give me false. So I could say right here, that's already a contradiction. P and C is going to be a contradiction, but to prove this property, we have to show that this conditional with that, false and false gives me a true, false and false gives me a true. So our equivalency shows a tautology, which means my property is proven. And my last one here, so I'm going to have P, and then all I have is not P's in tautology, so I'm only going to need 2 rows again. Try and make this one a little bit neater. So P, I'm going to need not P, I'm going to need P or not P, and I'm going to need a tautology, and I'm going to need P or not P biconditional with a tautology. So P, we have true or false. Not P is going to be opposite, so we have false and true. P or not P, so these two connected with an or. I have a true in both, so I end up with a true. Tautologies are always true, so my biconditional between those two columns will also give me a tautology, which means that our property is proven. Right? So let's say you made a silly mistake and you thought simple statement, and T is also a simple, or C is also a simple statement, so you did our traditional rows. So maybe you did P and C, but instead of doing 2 rows, you did 4. Right? Let's say you did this, and you tried to do our normal setup. Right? So we have first half true, second half false, but then you go to write it, and you're like, oh, contradictions are always false. So what you have here is repeating rows. You have the first 2 rows are the same and the second 2 rows are the same. So even if I continue on with this property, we did P and C. We did P and C and then our conditional. Biconditional with C. Even if I did this, right, P and C is still going to give me false, 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 and so we'll get true, 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 true. So you're still going to get the same table, and technically this is correct. It's just more work on your part. So it's seconds that you could have saved to do something else, to work on a different question, right? So again, think the number of rows is indicated by the number of simple statements, not the number of including contradictions and tautologies, just the number of P's, Q's, R's that you have, right? The simple statements. So these 2 rows here were unnecessary, didn't need to be drawn in. If I cross those out, I'm going to have the same table that I had above, just for a reference to save yourself some work throughout those proofs. Okay, so page 248, questions 1 to 40. Go through, try to prove all the properties. Again, the proofs, the truth tables for the proofs will be in the back of the textbook for all the odd numbered questions. And if you have issues with any of the problems, you're always welcome to pop into our live session and I can go through any of them with you. Otherwise, I'll see you for our last section in unit, what unit are we on? Unit 4, for chapter 9. So we're going to start with arguments in our next lecture. And that will be it for today. So have a wonderful day.